Okay, so today we're going to be talking about Rutherford versus the Bohr model of the atom. And the idea here is that we're ultimately going to be moving towards looking at the modern way in which we have modeled the atom. And we're putting things together to get to that point and building on a base of knowledge. So, speaking of building on a base of knowledge, what you all see here is something that should be pretty familiar. This is the plum pudding model. And you may or may not recall that this was a model that was proposed by Thomson. Okay, so Thomson's plum pudding model. And you also know that it wasn't long after Thomson's plum pudding model was put forward that Rutherford changed the concept. So let's move to a different slide here. Again, you may or may not recall that Rutherford was the scientist who did the work with shooting alpha particles at gold foil and seeing how they deflected or bounced back towards the source of the alpha particles, or pierced right on through and kept going and hit the screen on the opposite side of the source of alpha particles. But it was through his work that was developed his concept of a nuclear model, or actually it was sometimes it's referred to as the planetary model of the atom. And the reason why we talk about it as being the planetary model is that it's not unlike the concept of having the sun, as our central part of our solar system, and then having the planets that are cruising around in different orbits around the sun, right? And so the idea here was that with Rutherford was you'd have a central core or a nucleus which contained protons, and then orbiting that nucleus were the electrons, which were in particular orbits surrounding that nucleus. And what he really made sure to, have us consider here, I can't make it go backwards. Huh? That's weird. I can't get rid of that mark. That's not a good thing. Anyway, he made us consider that atoms are actually mostly made up of empty space. So that was a new concept, considering that prior to that, everyone considered that atoms were dense, indivisible objects. So with the idea that there was this planetary model with the nucleus at the center, this begged the question of, so tell us a little bit more about the electrons. All right, and this was sort of the big question is where are and how are the electrons arranged? So this got a lot of people thinking, and in particular, a gentleman named Niels Bohr, who actually learned under Rutherford. But it was Niels Bohr who proposed sort of the next combination of things. And what's important to understand here before I step into what Niels Bohr proposed is the idea of determining something through indirect evidence. Okay, so let me just write this down. Okay, so we have this concept of indirect evidence. And I want you to think about this because it's going to be very important when Niels Bohr went about determining where the electrons were. Obviously, Niels Bohr had no way of seeing this directly because atoms and in particular electrons and protons are way too small to be able to visualize. So all his ideas had to come up through indirect evidence. So let's just imagine a really simple concept here. Imagine I have hanging down this curtain. You can't see what's on the other side of this curtain. Imagine you don't peek, so you can't see what's on the other side. But you happen to, or there happens to be, without your knowledge, on the other side, there's I don't know what I guess I would call this a trash can filled with water. Okay? So then what happens is you take a baseball, say, so So let me go ahead and put the seams on our baseball. Oh, isn't that awesome? Wow. Oh, shoot. I hope I can get rid. This is so lame that I can't go backwards. What? This is just so strange. I can erase it, but I can't make it disappear. I'm using a new screencasting software, so oh well. Imagine that I were to, without peeking, I were to toss this baseball without knowing what happened into there, and it happened to land in the water, but I didn't know there was water behind there. And then somebody who was standing on the other side reached down, picked up the ball, and threw it back to me. Well, guess what? The ball would come back to me, it would be soaking wet, and I would know without direct knowledge that that water had somehow gotten wet because there was some water back there. All right, so I used indirect evidence, which is the wet ball, to indicate that there was water behind that curtain somewhere. Now, that's exactly how Niels Bohr went about figuring out where electrons were in his model of the atom. So let me skip ahead another slide here. Okay, so recall a couple things that we have here. And this all happened in 1911. This is when Bohr sort of put things together and figured out his ideas. And don't forget, the other day we talked about line spectra when I had you guys do that group challenge. You were looking at these light bulbs of sort. They were actually gas tubes. And when we excited those gas tubes and looked at those funky triangular scopes, we were able to see that depending on what gas you were looking at, it had a specific fingerprint with regard to its line spectrum. So no gas had the same line spectrum as another gas. So helium is going to look different from hydrogen, is going to look different from neon, etc. All right. So, and we understood this concept because if you were to take this tube of gas and you sent electricity through it and charged up that gas, which consists of atoms, we understood that at some point we know that we're exciting the atom in some sort of way, and that when it ceases to be excited, the energy that's released from the whatever the particle is that drops back down from the excited state is going to release a certain wavelength of light. Okay, so that means that if hydrogen is slightly different from neon, which we know it is, and has a different set of particles, that it's going to be excited in a different way than the hydrogen, and therefore emit a different set of wavelengths of light. And that's how we would distinguish between the line spectrum for hydrogen versus the line spectrum from neon. Okay? Now, we saw this phenomenon back in 1911, but we didn't understand what was going on behind these observations. So we had the indirect evidence, but we didn't know really what it was. We didn't understand what was behind the curtain. Okay, so what Niels Bohr did, let me go ahead and erase this really hideous looking drawing here. Okay, so what Niels Bohr did was he took a whole bunch of information and put it together to come up with this concept. The first thing was that he went to a lecture that was being given by Rutherford, where Rutherford was describing the planetary nature of the atom. Planetary, did I spell that right? Planetary, that's an R, that's a Y. Okay. And so that's when Bohr understood that there's going to be electrons cruising around in orbits around a nucleus. Okay. The other thing that Bohr picked up on was something that I had you guys research the other day when you were doing your group challenge, which is Planck's ideas of quantization. Okay, and don't forget, this is the concept that I referred to as being like energy in being more like steps than a ramp, where you can have certain energy levels or release of energy, and they're not sort of incremental. That's changes that shift from one point to another fairly dramatically. All right, that concept of quantization is an important thing here because that really helped to have them put things together. So I'm just going to remind you with quantization, it's like this. You have a set of energy that is here, and then you have another set of energy that's different up here, and another up here, another here, and another here. But you don't have things in the middle. There's a sudden bump up to the next step of energy. Okay? Oh, God, I suck. I can't believe I can't get rid of that thing. Sheesh. Okay. And then the third thing was that Bohr looked at those line spectra that I was just referring to moments ago. Okay, those fingerprints for the elements. So he took all these things, he pulled all these concepts together to come up with his concept, which fits all this indirect evidence, and therefore it makes sense, or it made sense to Bohr to propose a new model for the atom, and that is the following. So, just like Rutherford, Bohr said that there was a central nucleus of positive charge. But unlike Rutherford, who basically proposed that there was a cloud of electrons that were cruising around this nucleus, and he wasn't entirely sure where they were, other than the fact that they were cruising around in orbits like planets around the sun. Well, Bohr took it a little bit further, and he actually used the idea of Planck's quantization to come up with the idea that there were levels of energy that existed around the nucleus. Levels of energy. Now, this is a really important thing because he called these levels, fortunately for us, level 1, which is the ground state, level 2, n equals 2, n equals 3, n equals 4, and it could go on and on. Okay? But each of these levels represents a certain quantum number. Okay, quantum number, following the idea of quantization of energy, proposed by Planck. Okay, and that an electron, you could imagine that it would be found maybe at this ground state with quantum number 1, okay, level 1. And if you energized it by putting electricity through it or bombarding it with photons of light, whatever you wanted to do, you could imagine a moment where the energy associated with that electron would boost it up to the next quantum level, to state number 2. Well, it wouldn't stay up there because it wouldn't be able to sustain that energy constantly. And so eventually it would lose its energy and it would return back to its ground state. And in the process of returning, it would release a particular photon of light. All right? And it would be different if you had, say, an electron that was out here and it gained enough energy to, say, go all the way out to this level and then eventually return back down to this. This would be a very different wavelength of light that would be emitted. So if we call this one wavelength Pete, this would be wavelength Joe. Okay? So you'd have a different color that would be emitted. Silly that I wrote Pete and Joe, but I didn't know the exact colors associated with those things because I made it up. So imagine this now, how this fits in to Rutherford's concept of planetary nature of atoms. So we still have electrons orbiting a central nucleus, but it includes Planck's concept of quantization, which had just been proposed, and it also very importantly, helped to explain the phenomenon of line spectra associated with particular elements. Okay? So there you have it. Bohr's model includes these quantum numbers, which are essentially, think of them as being like levels of orbits surrounding the nucleus. And as you go further away from the nucleus, those are higher energy levels. Okay, higher energy levels away from the nucleus. Okay, I'm going to stop there, and hopefully I can figure out how to send this to you. See ya.